These last two sections in chapter 4 are going to be dealing with polynomials, and specifically the zeros. So this section we're going to be looking at the real zeros, and then in 4.6 we're going to extend that into the complex, so the imaginary numbers. So this section 4.5, there's going to be a lot that's going on. So let's go ahead and get started. Okay, example 1, let f of x equal x squared minus 2x plus 1. We're going to divide by, or f of x by x minus 1. So let's just use synthetic division. We're going to be using synthetic division quite a lot because it's quick and faster than regular division. Okay, so drop the 1. 1 times 1 is 1. Negative 2 plus 1. Negative 1. Negative 1 times 1. Negative 1. And then 1 minus 1, that is usually 0. All right, so my answer is always 1 degree less than what I am dividing. So that's going to be x minus 1, and since that's the 0, there's no remainder, so there's no like little fraction that we saw like in section 4.2 and 4.3. So x minus 1 is my answer. So part B, what is the remainder? Well, this last number, that's your remainder, so the remainder is 0. Okay, C, looks like a totally different type of question. So f of 1, if I plugged 1 in there, 1 minus 2 plus 1, that's also 0. Well, that's interesting. I kind of have a little relationship between what I divided by and when I plugged in a number. Well, that's going to be the remainder theorem. So if f is a polynomial, if you divide it by x minus c, then the remainder is f of c. So if you're just interested in the remainder, you can just plug in, what makes what you're dividing 0 into the function, and then whatever you get, that's your remainder. So example 2, what is the remainder if this polynomial is divided by x minus 2? So yeah, you could run through this synthetic division or just use that. So x minus 2, what makes that 0? 2. So plug 2 into your function, the polynomial, and we get 16 minus 12 plus 2 minus 5. And if you total that up, you get a 1. So that is your remainder. All right, moving on. Now we have the factor theorem. It's like, okay, well, what on earth would the remainder theorem be useful for? Well, something like this. So we're going to let f be a polynomial. So x minus c, it's a factor of that polynomial if and only if f of c is equal to 0. So if that remainder, if you plugged in, or what you're dividing by, if your remainder comes out as a 0, then x minus c is a factor. Okay, so example 3. Determine if the given binomial is a factor of f of x, and if it's not, what is the remainder after dividing? Okay, so we're going to start it out just the same way as example 2. Plug in what makes this thing 0 into the polynomial. So that'd be 8 minus 48 plus 24 minus 8, and that equals negative 24. Well, that's not 0. So in order to be a factor, the remainder has to be 0, and in this case, it's not. So not a factor. And then if it wasn't a factor, they wanted to know what the remainder was. So the remainder in this case was that negative 24. Okay, part B. I'm going to use the 2 again. So plug in the 2 into your polynomial, And we end up with 64 minus 60 minus 4, and that does equal 0. So since it's 0, x minus 2 is a factor. So x minus 2 would evenly divide or go into that polynomial. Okay, let's keep going for just a little bit longer, and then we'll take a break from this. So we have a theorem that talks about the number of roots or number of zeros a polynomial can have. So if it has a degree n, then it has at most n real zeros, and not over that. It can be under, but it can't be over that degree. So in example 4, how many real zeros could it have? So if you look at the degree, the polynomial could have as many zeros as the degree. So in this case, you could have 3 real zeros. You're not guaranteed to have 3 of them. You might have 2 or just 1, but you could have up to 3 real zeros. For B, oh, there's the degree. The second term, it's not written in order, so just be careful. Might be a little sneaky and tricky on you. So the degree is 11, so it has up to 11 real zeros. All right, let's go ahead and stop the video here, and then the next one we'll discuss the rational roots theorem and how to use it.